just to put in perspective, we're going to talk about visualizing Kubernetes environments. You'll know what I mean when I get into it. This kind of follows on from our previous webcast. If you've been on other ones, we've talked about the analysis of Kubernetes resources and the risks and the inefficiencies. And I'm going to cover some of the intro stuff that would be similar to our last webcast, but it's going to start getting cast in a very different way because we're going to make it all visual today because it's a new feature that we're bringing out within weeks of now that we're going to walk you through, and I'll be doing a demo. So a major part of today's will be a live demo, which always makes it exciting. I hope the demo works properly. So let's dive right in. And Danielle, make sure you let me know if there's any audio issues because we have been having some issues with my mic. So for those of us who do not know who we are, Densify we're an analytics company. We do resource optimization. You can think of it as continuously balancing supply and demand. We do it for virtual environments, cloud environments, and of course, container environments, which I'm talking about today. And that's very interesting because if you look at the progression that we've gone through in the market, and we like to kick off with this slide because I think it puts things in perspective. What we're seeing, especially as we go into containers, is more and more moving parts, more and more complexity. And I'll cover this in some detail. But as you get to the right, we're seeing that customers that are running containers, and we're analyzing a lot of container environments. Again, there's more granularity, there's more dynamics, there's more settings. I'll talk about all these things. And we're really shifting from a world where in virtual environments, we worried about VM placement, resource allocation, managing the pipeline, buying hardware early enough ahead so you'd have enough on the floor. We shifted to cloud where you don't need to buy so far ahead. It's more about choosing the right thing from the catalog, making sure it's elastic, and what we call micro purchasing, where I can buy small bits at a time. I can buy one server or one piece of a server at a time, which really changed the behavior. And now we're seeing that go even further where it's even more granular, it's even more dynamic, there's more complexity as far as the structures that you can run. And all the containers run on nodes, which are either cloud or virtual or physical. So it's kind of a multi-level approach in containers. So it's just becoming more and more complex. And what's happened is we've kind of shifted in the market from, a world where there were capacity management teams that were very disciplined around supply and demand. We saw a bit of a break there where people started using cloud and just reading the bill and really focusing on the bill and not what they're buying, but how they're buying. So people were buying the wrong things, the wrong sizes, the wrong types of instances, but focused on what they're spending and trying to get their spend down and buying RIs and things like that. But we see that kind of picking up again now where people are more focused on what they're buying, the actual resources, how they're using them. And we kind of nickname that capacity operations. We have a paper on that topic where it's kind of a more dynamic form of resource optimization. That's more elastic and more dynamic. And we think that's what's needed to get in the container world because they become highly dynamic. So just a bit of background on kind of our thought process. I'm going to stick to the right-hand side of this diagram today, and I'll come back to this diagram later. But we think as it gets more complex and more dynamic and more scaled, automation is key. So we have a big focus on automation and making sure that you come up with answers that you can actually automate. It's not the main topic today. I'll talk about that briefly. But the topic today is visualization. And again, as you get to the right, we're also finding it's really hard to understand what's going on. If you have hundreds or thousands or tens of thousands of containers, it's extremely difficult to understand just visibility. It becomes a challenge. So that's kind of the topic we'll focus on today. If I go into a container environment, and again, if you've been on our previous webcast, you may have seen this slide. The problem with containers is that you do need to give them resources. They're not magical. They're not actually even overcommitting like a virtual environment. So if you get it wrong, they're kind of unforgiving. So you have to give these requests and limits. In Kubernetes, ECS is a bit different, but we have to ask for memory and CPUs, how much we want at a minimum, and then what the limit is. And the problem is it's very hard to set these numbers. And maybe people don't know what they're doing, maybe they're guessing, but it's also if you don't have the right analytics and the right telemetry, you don't know what to set them to. And so people generally err on the side of making them too big. And so what happens is when the containers get deployed in the Kubernetes environments, the Tetris block kind of represents the utilization pattern, and the dotted line is the allocation. So we universally see that people are giving these too much resources to these containers in general. Now, it's much more nuanced than that. I'll go into it in much more detail, but in general, we find people are kind of over provisioning. And when you look at an actual environment, and we see this pattern everywhere, if you look at a Kubernetes cluster, the CPU in this case is being given out to the containers. 80–90% of the CPU resources are being deployed to containers, but on average, they're about 7% utilized. And it's odd, we see 7% as a number in a lot of places. It's kind of the magic number. So by deploying these resources, but not setting those values accurately, you end up having a lot of hardware on the floor that's not being used. And the problem is that these aren't virtual CPUs, they're actual real CPUs. Kubernetes doesn't virtualize things. So if I give you 1,000 millicores, they're yours and nobody else can use them. So you end up stranding a ton of capacity, which leads to cost. And we're seeing people start to realize that these Kubernetes environments are expensive. We talked to a lot of people that don't even know yet because they haven't deployed enough to really know, or they're not looking inside them to see what's happening. So it's very early on, but when you do start to run the analytics against environments, you tend to see this pattern, is what we find. And that's what we find, but what we're gonna ask our first poll now, it's one that we've asked in the same question in numerous webcasts, is do your container clusters look like this? Are they well utilized? Are they poorly utilized? I have no idea is a fine answer. Again, we find people might be running environments, but they've just deployed them and they haven't looked at what they're doing yet. Anyway, to answer the question, we'll see what the distribution is. We've asked the same question across several webcasts. And again, we see, looks like the results are kind of interesting. So some people are saying that they're better. Some people are saying they're well utilized. That's great. And a lot of people are saying they're not sure yet because they haven't deployed yet. So again, a mix of answers. We've had people in the past say they look just like this example. So it sounds like people attending the webcast are a little bit better than that, but we do see that as an issue. So I will continue on here. And I guess we're just sharing the results now so you can see them. And Danielle, I believe these will be shared afterwards as well.
Yes.
Okay, so that's kind of the setup we see now. I don't want to dwell on the today. I'm actually not going to dwell on the underutilization. I'm going to talk a lot about things that are too small as well. So when we analyze these environments, and I'll just spend a second on this, we look at the containers and the pods and the deployments and analyze the workload patterns to figure out if they're sized properly. So here, for example, this is a list of, these are containers that are often organized into pods, and there may be more than one of them running, and we just have one analyzed selected here. So there's a long list of these. And at the bottom, we can see the curves of what this thing is doing. And if I zoom in on that, this is a 24-hour view by quartile, in this case of the CPU utilization. So this thing's using about 1,000 millicores, peaking at about 2,000 or 3,000 until midday when it looks like it has 4 hours of higher activity, and it goes down again. So there's kind of a mountain of analysis happening under the covers for all the structures, all the containers and pods in the environment. And this is what one of those looks like. So I'm right down at the elemental level. This one, the requests are the yellow line, the limits are the purple line. So this one actually has a request and limit set to the same value, which isn't usually desired. It means that you're kind of very rigid. There's no overcommit in Kubernetes terms. You can't go above that line, and you're always allocated for CPUs, which is quite a bit of CPU horsepower, whether you're using it or not. So if you look at this, this pattern, especially at the highest point of the day, we're suggesting the request should come down, the limit should go up. You don't want to have the limit too low, or you'll constrain the resource. And this is all driven by policy. And I'm not going to talk about policy today, but there's a whole lot of settings that can go into how exactly I want to treat this. Do I want to be very aggressive? Do I want to be very conservative? Is it production, non-production? These are the kind of things that come up when you're running an environment. So if it's a production workload, I want to treat it very carefully and make sure it has enough resources, but not too much. And again, this goes in both directions, and I'll be talking about that. If I look at the net, I'll just spend a second here. What these numbers are saying, you don't have to try and read them all. The blue means we've got too much, and we get too much, we have to take some back. The orange means we have to give out more resources. So in this case, the request has to come down, the limit has to go up. I'll talk about memory later. Memory has to come down. And it nets out to be overall, usually, again, you have too much resource on the floor or too much in the cloud. So I'll circle back on that. That's kind of a fundamental primitive of our analysis. We do that for all the containers. That list can be thousands, or we have customers with 28,000 containers being analyzed. And right down at the detailed level, it's coming up with very specific recommendations for each one to get it right. So what that looks like when you get it right, if you do what I just described, it will analyze all the machine learning. We'll look at all the patterns and say, okay, we need to tweak these numbers up or down. Usually when we start running, it's usually downward, but a lot of times it's also up. When that happens, if you watch the bottom of the diagram here, when the pods get redeployed, the request values are much more in line with the actual needs of the workload. And when that happens, Kubernetes can automatically put more on each node. It just, Kubernetes works well to schedule, but if you give it garbage in, it can't do a good job. And I'll talk about that a bit, because if you get these numbers wrong coming in, Kubernetes doesn't know what to do. If you give it a request that's way lower than what you actually need, Kubernetes doesn't know what you're actually going to do. It just knows what you're requesting. So it will schedule you on a node, and you might have problems down the road. So these can be too high, they can be too low. Generally, if they're wrong, Kubernetes does what it can and might make a bit of a mess. If you get it right, it'll be clean and tidy like this. And then you can also go and say, well, the nodes, now that I've optimized it, I don't need as many CPU resources, or I don't need as much memory resources. So a lot of times we'll see, once you've optimized the containers, you can also optimize the nodes that they're running on. It's kind of this two-step win. And I'm talking about cloud here. On-prem looks different. If you're running in, on VMware, if your nodes are running in VMware, then it starts to, there's also optimization there, but you don't have infinite capacity like the cloud, but you do need to optimize those nodes as well. So we optimize, we get the right numbers, we get, and then we can kind of make it run more efficiently and low risk at the same time.
Andrew,
I see a question come in.
Yeah, there's a question for you right now.
So the question is, does a container provide suggestions based on the pods, or does it recognize a pod container as being part of a deployment? How does it affect HPA? So it does recognize the deployments and the pods. I'll show this when I drill down. The recommendations are for what we call manifested entities, or it's almost like a launch configuration. So we will give individual recommendations for containers linked to the pod, because the pod is often then the unit of deployment. So and this one, for example, on screen is a pod that has 2 containers inside it. So we give individual recommendations, but they're packaged up, and you'll see the different levels in the UI. It'll be recognizing pods versus containers, and then how many replicas of them there are, and all that type of stuff. So, and it does recognize the deployments. Again, you'll see that in the UI. Now, as far as HPA is concerned, yeah, it will. I mean, it will see the things that are being launched, and then it will come up with a composite recommendation. So if we see a structure that's being duplicated, it will say, well, they're all at the same launch configuration. So that configuration has to account for all the workload we saw in all the instances of it. So it does roll it up fairly intelligently to say, yeah, I have 30 containers launching off that same configuration. I look at all 30 and make sure that whatever's in the configuration matches them to give one answer, because of course you can't give 30 different answers for the replicas. And again, feel free to ask questions as I go, especially when I get into the demo. We'll try and keep it interactive. I'm going to keep cruising here so that we get to the demo. Now, one of the goals of this is to automate, like I said, so I just want to talk for a second about automation. When you get the answers correct and you have detailed policies and models that kind of look at all the patterns and all the peaks and all the valleys, say, okay, I now trust that answer, you can just do it. And in container environments, we think that's pretty important because there's so many containers, you don't want to do this manually. So automation is key. We do have Terraform modules and different modules to do integration for automation. And I'm just showing a customer example now, I'll just build the whole thing out, where in this case, part of their pipeline, they just hit our APIs, get the numbers, put them in the OpenShift templates in this case, and it deploys automatically. So again, there's a case study on our website if anybody's interested in a video about that. But it's just a good example where humans shouldn't be coming up with these numbers. It's just a waste of their time. You should just be looking at the numbers that are of the running environments and then intelligently coming up with values and deploying them in the pipeline. You might have change management around this or not. We do support that as well. In this particular case, I think they just got pre-approval to set them to whatever the analytics said, because they deployed and kind of tested the analytics and they trust it. So that's kind of, in our view, the ultimate goal. Back to those curve slides, as we get deeper and deeper into containers, this should just be automated as part of the pipeline. But again, that's not the topic for today. That's the automation. What I want to talk about is visualization. So what we've been seeing, we've been analyzing a lot of environments, big and small, and it's kind of a combination of effects. Like I mentioned, there's increasing scale. Again, we see customers. One customer recently we were analyzing had 28,000 containers and across data centers and all these things. There's a ton of them. And if you combine that with the fact that there's a lot of settings that you need to set here, they're actually more complicated than a VM. It's not just CPU and memory. I have to do requests and limits for both. They can be too big, they can be too small, they can be not set. All of these have different impacts, and I'll go through this. And again, there's more of these things to be set. and they don't overcommit. So I can't get it wrong. I can't just give everything 2 CPUs and say, well, when you're not using it, somebody else will use those 2 CPUs. The containers don't work that way. So scale and complexity means we can get the right answers like I showed in the previous slides and automate that, but it means people might not know what's going on. It's actually a bigger problem just saying, I don't even understand what's happening in this environment. And back to the poll question we asked, it may be that even people on this call don't actually know what's happening in the environment, because it's really hard to figure out when you have that many moving parts. And you can't just look at Grafana charts for individual containers. You can't see the big picture that way. So we kind of started to realize that, no, we need a way to look at this differently and understand what an environment is doing. So we came up with what we think is a very simple yet powerful way to look at this. And it's a histogram. You can think of it like it's almost like a bell curve. It's like a frequency distribution of your containers. And so let me just kind of explain carefully what this is saying, and then I'll pull it up live in a second. So up the vertical axis is the number of containers in each bucket. And as I go across from left to right, you see that the green is great. It means the container from memory is sized as it should be. If I look at the memory utilization and what's in the manifest, they're good. You're good. So there's a green bar. Left is too small, right is too big. Hopefully that's kind of intuitive. And the further you go out, and gray is not set, which is very important. So there may be ones that aren't set at all, which is generally not a good idea. There may be reasons, but typically they're not necessarily. Usually we see our customers intending to set these values. And so you can think of the red as kind of the dangerous and the yellow as the wasteful. Yellow, if you have a lot of yellow, you're going to spend a lot of money because you're going to deploy resources that aren't being used. And at the far right, you see 500%. That means you have 5 times more memory than you actually need. And we see that, like that's actually out there. The 200% means you have twice as much memory as you need. 100% means you're good, you're right on. And to the left, 20% means you have 1/5 of the memory that you need. And again, we actually see this in environments when we analyze them. So it may be that overall, on average, you're not bad, but it's the spread that's important. It's like a bell curve, and being way out in the edges of it is not good. It means that you're either wasting a lot of money or you're incurring a lot of risk. And the idea is we want to kind of sharpen the curve and get everything into the green and get rid of that gray at the same time. So we find that this is a useful visualization because you can kind of glance at it and see what's going on. Again, the averages don't give you the right picture. Even if I'm told I have 50 containers that are too big, I don't quite see what's happening. With this, I can tell you what's happening pretty quickly. I like to kind of joke, it's like a Rorschach, like an ink blot test for your data center. Like that's, look at this and tell me what you see. It's like reading the tea leaves. And in fact, we're going to be coming up with names for the patterns we see as we run this more and more and generate these visualizations, because again, you do get insight into how the pipeline is working, what is actually happening. You can see that in the patterns of these charts. So I'm going to go through a little more detail on that and I'll pull the demo. I was going to do this in the demo, but it's easier to explain with PowerPoint. But this is exactly what the demo is. So let's talk about each of the resources and the so what factor of these different colors. So if I'm looking at CPU requests, so here we have 432 containers that are in 310 pods. And again, a lot of times you see a lot of pods are one container, but in this case, there's some with multiple. And if I break this down, so the green means the CPU requests are in line with the patterns. And it looks like there's about 140 of them that are okay. So it's still only 1/3 of the environment is correct. This environment doesn't look that bad, but still 2/3 of the environment is wrong. The red means I am not giving enough CPU resources to the containers. And if there's too much red, you can have throttling issues. So if your nodes get oversubscribed for CPU, because you gave it all out and there's none left to use, you could. So let's put it, if I continuously ask for not enough CPU resources for the pods, they'll get overstacked, and then the node could have contention. You might get slowed down. So that red zone is a throttling risk zone. The yellow zone is a kind of a cost zone, where I'm just making them too big. And the spike at the right, we see that quite a bit, where a lot of things are just way too big, and so they're just tying up resources. That's where your costs are going to come from. And again, I want to stress, you can have both risk and cost. This is a real environment. You have both risk and cost in the same environment. The gray means Kubernetes really doesn't know what to do with it when you give it to it. So it's going to try its best. It's going to throw darts, put them on the nodes. And we see that leading to big node imbalances, where when the workloads actually run and they're not what you asked for, some nodes can be high load, some can have almost nothing running. We see that creating issues in customers as well. So all of these are an issue. And again, we're seeing not a lot out there correct. There's not a lot of green, and I'll show you in some environments there's no green. So this example, overall, we're 30% over, 29% over on CPU. We're asking for too much CPU, but again, that spread is what's important. We're actually, even if we were at spot on, there's a whole lot of stuff wrong here, and I'll show an example of that. So that's CPU requests. We'll make available these slides, and there's a table that describes all this as well. I just want to cover this because it's important to understand why we don't want to be out in the wings of this diagram. So memory, okay, I think we probably understand what that is. Memory being too low creates a bigger risk than CPU. So CPUs can be throttled because they're compressible. Memory isn't. So if you don't ask for enough memory for your workloads, a node can have memory pressure and you will get killed. And usually the things at the far left of this diagram are the first to get killed. So you do not want to have too much red. Again, even if you're overall, you've given out too much memory, you might have pressure on certain nodes or in certain environments. So red is the killer zone. Yellow is the stranding waste zone. You're just going to spend a lot of money if you give everybody more memory than they need. And again, unspecified just creates the risk that Kubernetes does a poor job placing them, which can lead to contention and conflict on the nodes. So generally, you do not want to leave the memory settings unset. CPU memory, those are requests. I'll talk about limits for a second. Oh, and overall, this environment has too much memory, but again, it's got a lot of red. It's complicated. So even an environment that has a lot of waste and is wasting a lot of money, we usually see red in there causing problems. Now I see a question coming through. Does the basis of the analysis is a daily peak usage, I assume separately from MCPU? Do you average your peaks over each hour? How do you handle min or sec level spikes? So it's back to that quarter. The model is very detailed, so it's not hourly peak. We build an hourly, not daily peak. It's an hourly model by quartile. So we'll see the min and the max and sustained activity every hour of the day, and that's the basis. So we actually keep the pattern throughout the day, and the policy can let you then use that. You can say, if I'm only going high for 2 hours, maybe I don't need to bother giving all those, requesting those resources. Or the policy can say, no, I want to go to the peak or the sustained activity. So it's a very detailed model. We can go back through all the days of history and say, drop the top and bottom 5%, build a model of the composite workload, take the hourly numbers and do this with it. So I won't get into that, all those details today, but it's a very powerful workload analysis model. Again, you don't want to just go off daily averages or peaks, and even hourly averages and peaks. We're much more detailed than that. It actually uses a quartile-based distribution model to understand. Because again, you might say, well, that can go to a burstable instance because it has this pattern of activity. So we get down to that level of detail. And I'll go back in the demo, I'll pull up those slides again and kind of reinforce that. Limits, CPU limits, they're mildly interesting. We don't see a lot of, if you're green, obviously you're good. We do see some red. If you put the limit below your utilization, you can be throttled. So you kind of don't want to be in the red. We don't see a lot of stuff in the red here. Too high means I'm not constraining you. So if a process inside your container goes crazy, and this is important, we're not giving virtual CPUs to the pods. It's not like a VMware environment where you can only damage your VM. You can use, theoretically, all the resources of the node. So it's important to put limits on things. And we see the limits in this case being too high. Our policy stops at doubling the limit. So we don't see above 200 because our policy won't make that big a step. And there's a lot of gray here, meaning we're not constraining this, these containers. So there's 150 something containers that have no limit set. If they go crazy, then I wouldn't want to be on that node. You could see everything having problems. And we see that happening in environments when we analyze it. So CPU limits, there's really a noisy neighbor risk if you don't put limits on things and they're not good neighbors. Memory limits, same story. But this red is very dangerous. So I want to pause on this red. The out of memory killer, if you have pressure on a node, it will kill containers. And everybody's probably familiar with that. But also, if you have a limit, if your limit is too low, if you're using more memory than your limit, then the Linux kernel can kill you. It can come in and it'll kill a process inside your container. So when you have red here, it's extremely dangerous. And so we watch for this carefully. Any red in the memory limit zone means you are in imminent risk of being killed. And that's, again, I'll show you that in some detail. And we've seen that happen in customers where we've seen this. We've drilled down the long-term pattern and you can see the container getting whacked by Linux. So that's a big risk. So again, even in environments where we have a lot of waste and we're overspending, we see this kind of stuff happening under the covers. And again, in this case, that gray bar is meaning we're not setting limits. We've seen memory leaks cause a node to ramp up and hit the roof. That's because of that gray usually, that you didn't set a limit on the containers. So the analysis will recommend a limit so you don't have that problem. Okay, that's the kind of end of the PowerPoint. Oh, sorry, too high is the noisy neighbor risk. I'm going to cover these things. So I'm going to flip over now and show this live because we've now, I'm going to show you kind of a sneak peek at what we call version 14.1, which will be deployed to our SaaS team imminently and make its way to our customers. And I'm going to show you exactly what this looks like in the product itself. Okay, and Danielle, maybe you can confirm that everybody, you can see the, I'm showing my whole screen, so we should be okay. And I'm going to go F11 to get it nice and big. Okay, this is our user interface. If you've been in our product before, this might look familiar. If not, you see across the top here, public cloud, containers, private cloud, that's kind of the VMware analysis. I'm not going to go through those things now. This is a container overview. I'm going to go, or the cloud overview, I'm going to go right to containers. And here, when I drill down the containers, I'm just running against a demo environment. These are real workloads, but it's just kind of a demo environment. And so it's not too big. We have 432 containers. There's 212 container manifests in 154 pods. So I won't belabor that point. It's not a huge environment, but there's about 212 manifested containers that are contained in 154 pods. We're seeing a breakdown of what the analytics are saying at a high level, how many are just right, how many need to be bigger or smaller, or bigger and smaller, or set from nothing. I'm not going to sit here very long because that's a good roll-up of the entire environment and how much memory and CPU waste there is. But I'm going to start drilling down because I think, so we have this high-level view, and you might have hundreds or thousands of containers or tens of thousands of containers. This tells you the overall picture. But I want to go down a level deeper because that doesn't tell you the whole picture. It doesn't necessarily let you understand what's going on in that environment. Even if I say half of it's too big, half is too small, well, what does that actually mean? And of course, with a live demo now, for some reason, I'm getting a long load time here. Just give me a second to figure out why this is happening. It wouldn't be a live demo without something like this. Okay. Give me 1 second. I'm going to, okay, there we go. It's back now. I'm not sure what happened there. So, so I've gone down to the data. So I was at the summary tab, which gives me that overall donut view of all the kind of roll up of everything. And you see there's filtering I can do across the top here. I can filter down on various things, but that's what I'm going to do at this level. I'm going to get into the data. So I am now looking at it by business unit. So I have all these systems and I've broken them down by business unit. I'll go to some other ones in a second. And you see I have streaming services, new accounts, I have different business units. And there's the 212 manifests. And across these rows, let me just kind of describe this for a second. I can rank by the efficiency. So a red number means I'm running too hot. I don't have enough resources deployed for the workload. Something like 0.72 means I have too much resources deployed. I'm inefficient. So this is kind of where the costs come in. And we see kind of a mix here. I'm going to sort them by how big these environments are. Streaming service is the biggest. And again, they all add up to 212. So I'm going to click on this 212. So first of all, if I do this, I'm going to see the entire environment as a histogram. And these are the same histograms I just went through in the PowerPoint. But here they are live. CPU request, memory request, CPU limit, memory limit. I can just view them one at a time, or I can view the 4 of them together, which is usually once you start learning how to read these things, you just want to see all 4 of them. I'm going to view the unspecified. And so overall, again, this is what I described in the PowerPoint. We see things with too much, not enough across the board. And the net for this environment is we have 28% too much CPU and 15% too much memory. Now, from here, I can drill down. So first of all, you see that in this case, I have a lot of containers that have too much CPU. I can drill down. Somebody will probably ask the question. Coming soon, you'll be able to click on these bars themselves and see exactly these 59 containers. In the first rev, you click on the heading, and I will get a sorted view of the containers that are too big. And the top of this list is the ones that are unset. I need to scroll down a bit. So here we go. This one is too big. So like I showed in the PowerPoint, this analysis is telling me that for this, the CPU utilization it goes up and down. There's that hourly pattern with the peaks, and the blue zone is the sustained activity. So the workload is spending half its time in the thick zone, peaking up and going down as low as the bottom of the spike. So it's kind of like a candlestick chart of utilization by hour. We're never really going over a quarter of a CPU, but we're giving this thing 2 CPUs. And the request and limit are both set at 2. And of course, we're recommending, no, you should bring the request down and the limit, but we do it slowly. Like again, policy says, don't go too crazy, just bring it down and, like don't go more than half at a time. So we're seeing, this is the list of things that are too big. Again, this is another workload pattern. This workload kind of hangs pretty consistently around a quarter of a CPU, but we're still getting 2 CPUs, and on and on. And this is a long list. So again, this is all that detailed mountain of analytics. The histogram just lets me see that visually. I've got a whole ton of things that are way too big, some that are mildly too big, and I've got a bunch that are too small. So if I go to the top of this list, now this is interesting. So this workload is only a transient workload. It doesn't run for very long, but when it does run, it's way above its request. And so this could be intended behavior. It's all driven by policy. You can say, I don't want to request that much, or I do. This next one on the list is a little more clear. This is a kind of a sustained, it looks like a transactional workload that peaks up midday, comes back down, and we're only asking for 500 millicores. And based on policy, we're saying, no, we don't want to spend 6 hours above our request value. Let's ask for a little more CPU just to protect this workload. Again, if it's production, you might want to protect it. If it's dev test, I might want to go with a lower setting. But the idea here is that I've got all this detailed analytics that drives automation, as I talked about. But the idea here is I can just visualize that and see, okay, I've got too much spread here. I've got too many things out in the wings of the CPU and memory. The memory side, I've got memory risks. Again, I've got, you see, like if you watch this third chart here, this one's been given 25 megabytes. Again, it's really small. No, sorry, it's been given. I don't know what the number is. It's too small to read here, but it's the request value is very low, and it's using way more memory than that. So this is definitely something you don't want to happen. If I click my way down, you see all of these ones. The utilization is way above, and we're recommending on the far right, bump up the request values, bring down the limits, make this a little more in line with what we're seeing. And this can be based on months of data. Again, the policy says, watch this thing, watch month end, watch quarter end, and get the right numbers. So that's CPU memory. Again, the memory limit, like I mentioned, these red things are very dangerous. If I go down and drill down on those, if I see red there, and I click at the top here. So this is interesting. This is a scheduler. And so every few hours it lights up and gets busy for CPU and memory. And you can see it's going way above. The memory request is sitting at the base, but the limit is at 1,000 megabytes. So it's limited at a gigabyte, but it's going up to almost 2 gigabytes. So when this thing lights up, it could actually get killed. Like this, again, is a very dangerous situation where you're actually using memory above your limit. We're recommending the limit go up to the top there. And again, there's several like this in this list that are running. The memory is running above the limit, and it's a dangerous situation. So again, it's like finding the needle in the haystack of these workloads. I can look at this, and again, we do this against, we've done one environment of 28,000 containers in one visualization, and I just know where to look. I can go, I want to see if there's too much red in the top right. I want to see if there's any red in the bottom right, and I can kind of get a picture very quickly for what's happening. And again, there's a strong observability message here that people don't have any idea what's going on. This gives you a very good idea what's going on. So again, feel free to ask me questions. I'm just going to do a couple more things here. I was drilled down on the entire environment, but of course I can drill down on sections of the environment, and I'm just going to do that for a second. So I have a streaming services business unit that is, and this can be namespaces, it can be almost anything. There's 103 manifested items, and it looks like it's got too much, it's got inefficiency, so it's kind of wasting money. If I click down, we can kind of see why. So in this case, the yellow zone for CPU is bigger than the green zone, which means we've got a lot of stuff that's just way too big. In fact, we're 37% net on CPU over. So whatever this business unit is doing, whatever they're doing in their pipeline, they're getting the numbers too big for CPU, and they're getting them too small for memory. So the memory has a deficit of 6.9%, meaning there's just too many containers here, in the red. So we've got a bit of risk. We've got some waste. Net. If you net all this stuff out and kind of cost weight it, we've got waste here. We're wasting money. But under the covers, we also have risk, and we have memory risk as well. So if this is a critical business service, streaming services, that might be our bread and butter business unit. You do not want to see red in these memory curves. So I can see it very quickly. In this case, the CPU yellow zone is outweighing the green zone. We need to kind of get that back under control. So that's one business unit. Remember that the yellow is bigger than the green. If I go to the next business unit, and I hope you're starting to see here now. So business new accounts, it's about half the size. These guys are doing a much better job. The green spike is much bigger. We still have a ton of problem here. Like they are almost perfect for CPU. Like 4.7% is a pretty good number. They're giving out the right amount of CPU, but they're still getting it wrong under the covers. There's still some that are way too big and some that are way too small. So they're almost right for the wrong reason. And we see this quite a bit. We've seen entire data centers that look like they're good on average, but underneath they're almost all wrong. And even though this business unit is getting the CPUs pretty good, they're doing worse for memory. Their memory, they have some systems that are 1/5 the size they should be from a memory perspective. They have 10 containers and 22% deficit overall. So this group, again, it's like the inkblot test. You can start to look at this and say, yeah, I look at this, and this team, whatever they're doing in their pipeline, they're doing better CPU, worse for memory, a little better on limit risk, but there's still some limit risk in here. So again, hopefully everybody's getting the idea. I can click around. I can see, in this case, by business unit, this test unit, I have a tiny test unit that's running 3 workloads. Oh, look at that. They're doing a really good job. They're getting them all perfect. And that's where you want to get, is kind of everything in the green. So that's by business unit. I'm going to do one more thing before I wrap. I also, and this is probably one of the most powerful things, these are what we call a heterogeneous group. That could be a bunch of who knows what, database servers and queues and web servers. It's a mixed bag of stuff, and we can view it in one picture and see how it's doing. I can also go up here and say, well, I just want to view it by, let's say, container. And I get a completely different view. Now I get a slice across my environment of my containers. So for example, my Istio proxies, I have 43 Istio proxies running. How are they doing? Well, there's no gray. So what we call the hygiene is good. They're setting all the values, but the values are almost all set wrong. In fact, there's no green. For none of them are right from memory. If I drill down on these, they're all going to be wrong. CPU, looks like there's about 5 of them that are right, and the rest of them are all wrong. Then none of the limits are right. They're all set, but they're not good. So again, this is just, I can look at it by business unit, by app. I can look at, in this case, by container, and we find this is a very powerful one. Maybe I want to change my startup configuration to kind of, take into account all of these diverse running containers. I can look at the different view, NFS, all these different things. I think everybody gets the idea. This Nginx one is interesting. So if I click on the Nginx, they're all perfect. So they're all set and they're all correct. So whoever's deploying those containers is getting them absolutely perfect. And again, we see a mixed bag. We see a mixed bag between business units, between apps, between container types. That's the whole point of this, is that even if an environment looks pretty good on average, under the covers, it can be a bit of a mess. And that's what this visualization is intended to show. So hopefully that walkthrough gives everybody a good idea of what we're talking about here. We've covered these topics in other webcasts and gone into detailed analysis, but now we're saying this is a very powerful way just to see what's going on in an environment, and then be able to find, again, the needles in the haystack, be able to drill down and prioritize what you want to fix. So that is as far as I wanted to get in the demo. I'm hoping that made sense. I'm not sure where my PowerPoint went. Let me just bring it back up to close off. I think we had another poll we were going to do right now. Danielle, is that correct?
Yes, I'm just pulling that up now. Sorry.
Okay. And we're very close to the 45-minute mark, so we'll just put that poll up, and then I'll close off with a couple more slides.
Stop sharing. All right, there you go.
Okay, so I don't know if we need to share this. I'll just keep moving through. But I guess one thing that we find is that when we show this to people, people want to see their own environment depicted this way. So if anyone's interested in that, then just let us know. And the last thing I wanted to mention is we have a great partnership with Intel. So if you're interested in what I showed, especially on the cloud front, container front, there's a densify is the basis of what Intel calls Intel Cloud Optimizer. They have a program where they will fund its use for qualified enterprise customers for the cloud usage. They will fund the use of densify. So if you're interested in this, there's actually a very nice way to get it deployed where it's funded by Intel. So feel free to ask us if you're interested in that. We see a lot of people are, because of course the price is certainly good, being free. And that's the last slide I wanted to cover. Danielle, I think you were going to cover a couple more items before we close up.
I do. I'll quickly run through the next couple of slides just in the essence of time here.
Okay.
Okay, so thank you again, Andrew. I'm just going to take a quick look at the chat. I don't see any other questions. However, if you do have any that come up, feel free to email us at answers@densify.com or events@densify.com, and we will get back to you directly with a response. We do have a select few resources that may be of interest to you, and you can go ahead and scan the QR codes and you'll be directed straight to the download links. The first item here is Andrew's white paper that he had spoken about earlier. So he wrote a concise white paper. It's about a 10-minute read on capacity operations, and this may be useful as you think of the overall process in managing cloud and containers. We also have linked here the Raiffeisen Bank case study that Andrew also mentioned earlier in the presentation. And next slide, Andrew. Densify is hosting a FinOps-focused webinar in a couple of weeks on December the 8th. And this is a bit of a back by popular demand webinar topic, if you will. We did host a similar webcast a couple months ago. So if you are interested, do join us as we walk through what it means to optimize the finance tools you purchase in order to exponentially increase the results of your FinOps strategy. We will also be running through a demo as part of this session. And last slide, Andrew. We also welcome you to follow along on our social channels. So stay in the know with our future events and what's new on the blog, any latest resources, all via LinkedIn. And of course, check out our YouTube channel as we host a video library of all of our webcasts there. And with that, it concludes our event. Thank you again, Andrew, and everyone for joining us today. We do hope to see you at our next session, and enjoy the rest of your day.